Hello everyone, welcome to the class. Just give me one moment. I would check if I'm online. Right. All right. Okay, so let's begin today's class. In today's class, the topic we would be covering is basically your unit electrostatics. But in today's class, we'll be covering Gauss's theorem. All right. So that's the topic we'll be doing today. And once again, my name is Mohana. I'm a physics educator at Unacademy. So if you're taking ISC Board, right, physics for class 11 or 12 with Unacademy, I'll be teaching. And this is my Telegram group link. So before going live for any channel or if there's any update, everything will be shared in my Telegram group. So you can follow me through my Telegram group. At the same time, this is the Unacademy ICSE and ISC Board common Telegram channel. Okay, so you can follow this as well. Now, just like how we have free classes on the YouTube platform, we also have free classes on the Unacademy platform. So these classes are absolutely free. You can learn from any of your favorite educators, and you can engage with the educators via the pool feature. And since these classes are live classes, so again, if you have any doubts, you can get your doubts cleared then and there. And there is a link in the description. So if you just click on the link for class 12, if you click on that link in the description box, it will take you to the upcoming special classes for physics in the Unacademy platform, and you can just go click on the enroll button or to notify me button. So there, what will happen is that before the class would go live, you would be notified. Right. So the next class. So yesterday's class, we actually did current electricity, right? We did it with that in the YouTube class session. So you can go check out that video as well. Now, next upcoming special class, this classes happens on the YouTube Unacademy platform. Okay, will be on 11th June. This is going to happen at 4 p.m. Okay, and the next upcoming topic would be current electricity. So we started current electricity in YouTube. So the continuation of that I would do in the Unacademy platform. All right, but if you have any doubts, I'm there to again teach you from the beginning. Similarly, on 14th June, we are doing the concepts from magnetism unit. We already started part 1. So magnetism unit is being completely, as of now, it's being completely covered on the Unacademy platform. So you can just go back and register. You can just go back and watch part 1 video, and you can come to the part 2 class. All right. Part 2 would be on 14th. So you can come for this. And on 18th June, there will be in between these timings, right, from 14 to 18 and 11 to 14, there will be other upcoming classes. So on YouTube, we are doing electrostatic unit and current electricity. But in the Unacademy platform, we will be doing current electricity, that is your unit 2, and magnetism. These are the chapters that are getting covered in the platform as well as the YouTube channel. So these classes are absolutely free. You can just click on the link below to enroll for those classes. Now, in case if you're interested in taking the plus subscription, these plus subscriptions are, you can absolutely, these are like, you can learn from the comfort of your home. And whenever you're taking a plus subscription, you're getting an entire course. That is, you're getting math, physics, chemistry, and biology. You're getting 4 courses together, all right? And all the educators on the platform are good. So you'll be learning from top educators. We also have the live test series. So every other weekend, you will be attending a test, and there will be an analysis sessions for the same. So if you have any doubts, you can get your doubts cleared then and there. And there is an ongoing batch you can actually check out. And every 4th class, right, in the every 4th session in the plus course is a doubt clearing session. So first 3 days, whatever the previous 3 classes, whatever concepts you have learned in the 4th class, you can get the doubts clear. And in the plus courses, we will be covering your entire syllabus as well. Now, the pricing of the courses, as the number of months increases, the pricing per month decreases. Okay, so if you're taking a 1 month subscription or a 1 year subscription, then this is the amount you're paying per month, and this is the amount you're paying for a year. Okay, now in case if you're using my code MTIS10, okay, then you will be getting a 10% discount on the same. In case any class 11 students, if you're watching, if you take class level subscription is absolutely free for you guys. All right. Now, So today's class, in the previous classes we have learnt about the electric field, right? We have learnt what are the properties, the electric field line, what are the properties of the electric field lines. We have learnt what is electric potential. We've just learned the concept of electric potential. This class we would begin by learning what is an electric flux, alright? So before you learn what is an electric flux, you need to understand what is the area vector, okay? Now, if you take, right, if you take any area, okay, and if you draw a normal to it, let's say this area is basically given by this area. Let's say this area is basically, this is the area, and let's say this area is ds. Okay, now for this particular area, if you place a perpendicular to this area, right, if you have an area and if you place something perpendicular to this, then you will get the area vector. Okay, now so the area vector is nothing but the direction of the planar area vector is specified by a normal to the plane. Okay, when you say a vector, right, area is a scalar, right? When you say area vector, now if you want to specify it as a vector, then you have to give a direction to it. How do you do that? You take the surface, draw a perpendicular to it. Okay, give a perpendicular normal to it. That will always specify what is the area. Sanjit, hello Sanjit. Okay, that will give you the direction of the vector. Area vector. Okay, now this direction of the area vector, you can use it, you can say that this is a normal vector, right, or a unit vector. Unit vector always has a magnitude 1. Okay, so from this we can say this particular area vector you want to define, this area vector can be defined as, can be given as, right, the normal n cap, right, into ds, into the area ds. This will be your unit vector, the unit vector into the area ds. That will give you your area vector, right? If in case your surface is not very, let's say your surface is not uniform, right? Let's say you have a surface which is not very uniform. Then what you can do is you can take a very small surface, right? For that particular surface, you can draw a normal to the surface, okay? This will give you the area vector. Okay, now this is the normal to the surface, and this will probably give you the area vector ds. Okay, in this case, the area you're considering this, the complete area, you can take the complete area to be, let's say the surface to be s. The small surface that you consider, this could be ds. Okay, so in this case, what is the area? What is the area vector in this case? This ds, right, can be given as, this is in case of a surface vector, right? It could be given as n into ds. Right, n vector, that is the unit vector times the ds. What is the area that you've taken? Okay, this is very simple. You just take any area, draw a perpendicular normal to it, that direction, right? It is similar to saying that is the direction in which the area would be, right? So this is the area vector. Now, why should we learn the concept of area vector? Because you need to understand what is an area vector for you to define flux. All right. Now, flux is a property of any vector field. Alright, so when you're talking about electric flux, it is the property of your electric field lines. Alright, so the total number of electric lines, what is, as simple as possible, if you want to say what is an electric flux, what is the total number of electric lines of forces passing through a given area? That gives you your electric flux. Alright, so electric flux through a given area, right, held inside an electric field is a measure of the total number of electric lines of forces passing normally through that area. Now, let's say there is a particular surface, alright, let's say there is electric field lines which are flowing normal to the surface. Say there is electric field lines, right, passing through this normal to the surface over here. Actually, there is, you can also take it as, let's say there is some positive charge over here, there's some positive charges over here, right? If there is a positive charge, what happens? Right, electric field lines will always be pointed radially outwards. For a positive charge, electric field lines will always be pointed radially outward, right? So the electric field lines are coming in this direction. Now, in that place, if you place an area, vector, all right. Now, we can actually know how much field lines are passing through this particular area. That gives you your electric flux. All right. So you can say from here, you can actually say, if this is the electric field E, and let's say this particular area has a, let's say this particular surface, this particular area is given by delta S. Okay. Now, how many field lines are passing through this area? that gives you, that is the electric flux through a given area is what? Area held inside an electric field is a measure of total number of electric lines passing normally through that area. So electric flux, we always give it by a quantity delta. Okay, this is delta E. Through this particular area, okay, the electric field line that is passing through would be basically E into delta. What is the surface over here? Surface is delta S. For a given surface, how many field lines are flowing? That will be your electric flux. Okay, so this is basically your area, right? Now, let's say there is an electric field line going in this direction, right? In this case, the electric field line is E, right? This electric field line is going in this direction. But for this area that we have considered, if we are drawing a normal to the surface, how will that be? That normal will actually be, this is the area we have taken. So if I draw a normal to it, it will be in this direction, right? It will be in the direction of the electric field, right? That normal I will basically give it as n cap. This is a unit vector of this area, and area is given by delta S, right? This area is given by delta S. Now, if you take this as n cap, in this case, what you can see is there is no, if you look at an angle, right, between the area vector and the electric field, the angle is 0 degrees. Correct? So there is no angle between them. So here you can say that delta phi is equal to E into delta S. You can directly go with this one. That is, for the given area delta S, how many field lines are passing through? That will give you your electric flux over here. For a given area, how many field lines are passing through? This will give you electric flux. But generally, not all the time, the electric field lines, right, the area that you're placing in an electric field line will be perpendicular to it, right? Sometimes you will come across situations where the electric field lines, right, the electric field lines might be going in, let's say there is an electric field line that is going in this direction, okay, and you're placing the field in to it, right? Let's say the electric field lines are going in this direction. Now we are placing a field over here, right? Now the electric field line makes an angle with the area vector, right? The electric field line is actually making an angle with the area vector. Now here we can say the electric field lines are going in this direction, right? So the electric field lines in this case are going in this direction, right? And this surface is what? This surface has an area. Let's say the surface of this area is basically, we can say the surface of the area is delta S, right? That is the surface of the area. Now the electric field line, so for combined, I'm just taking one single area on this, in one single, here you can see this, there is a number of electric field lines going over here, but we are just taking one single line, okay? So for a given electric field, let's say the electric field is going in this direction, okay? Now for this particular area, where is the electric, how will be the normal to it? The normal to it will be in this direction, right? The normal will be given in this direction. This will be the area vector, right? And this, let's say this will be your area vector, okay? This is a unit area vector in terms of, you're giving it in terms of the unit vector, all right? Now in this case, this particular electric field with that of the surface, it's at an angle of theta, right? It's making an angle theta. Okay, this electric field E with the normal component of these with the surface vector, it's making an angle theta, right? So in this case, if you want this angle over here, if you want, say this is basically, you can take it as a right angle triangle, right? Now what will be your delta phi? That is the electric flux. Electric flux will be what? Normal component of E, right? That will basically be your normal. What is the normal component of E? E, right? A normal component of the electric field times, right? Normal component of the electric field. That's what we did in the last class, right? We took the electric field. The electric field was normal to the area vector. There was no angle between them, right? Now, so we want to take, in this case, there is an angle. So we have to find what is the normal component of this. We have to find what is the normal component of the electric field and multiply it with its with the area, with the surface area. Okay, what is the normal component of the electric field in this case? How do we find it? Now you can use the trigonometry, right? But in this case, this actually looks like a right angle triangle, correct? So you can take this, right, just give me one moment, all right. So here you can make use of the right angle triangle, right? This is basically a right angle triangle. You want to take an electric field line that's in this direction. Okay, this is the electric field line, but you want to consider the electric field line that's in the normal to that of the plane. Okay, how many electric field line that is normal to this area vector in this side? Okay, how do we get that? We get that by taking, we can make use of trigonometry. In this case, we know it is an angle theta. So if you want this normal component of the electric field, it will be what? In this case, it will be adjacent with your base to the hypotenuse, right? So it will be cos theta. So this angle over here would be E cos theta. So in this case, when your electric field line and the area vector are basically at an angle, then we make use of this normal component of the electric field. Normal component of the electric field is E cos theta, right? Into what is your surface area? Surface area is nothing but delta S, right? And this delta phi, that is flux through this particular area, okay? That is basically given by delta phi. This delta phi would be equal to, since it is a it can be given in terms of a vector quantity as well. Okay, so in this case you can give it as, because electric field is a vector, so E vector dot area vector, this is also a vector quantity, you can give it as delta ds. Okay, so you have one more. In case if there is an angle, then you have E into delta cos theta. So in that case, delta phi meaning the flux through this area is given by E delta S cos theta. Okay, now normally the surface, if in case the surface is, if in case you're taking a very ununiform surface. Now till now whatever cases we saw was for uniform surface, right? If you see the surface itself is extremely uniform. One case we saw the area vector, there is no angle between the electric field and the area vector, and in the second case we were able to see the electric field lines. What of the electric field lines make an angle with this area vector over here? Right. So the next thing is, in case, what if the surface that you're considering is extremely abnormal? Sorry, the surface that you're considering is actually quite, let's say, you have a surface like this. Now this is a non-uniform surface, right? In such a case, what we usually do is, we actually take a very small surface. Okay, and we're going to see, let there be how much of field lines are going through this entire surface, how much of field lines are going through, that's okay. But we are going to take a very small region and we are going to draw a normal to that region. Okay, now the normal to this region, let's say the normal to this region is basically n cap. Let's say the surface, this is the surface, the entire surface, let's say S. The small element, the small surface that you're considering, this particular surface will be ds, and n is the normal to this particular surface. Right now, let's say the electric field lines are going in this direction. Okay, throughout the surface, throughout this entire surface, there is electric field lines going everywhere, but we are interested only in the electric field lines going through the small area. Okay, let's say that, let that be E. Now, now you can actually find, okay, now if you know this, you can actually find what is delta phi E, right? Delta phi E is what? Delta phi E will be how much field lines, electric field lines are going through this vector, this area, right? And it makes an area theta, right? Through this phi, through this delta ts into cos theta, right? Into cos theta into this area. This area is basically ds. So delta phi E will basically be what? E cos. Right, so this will be, let's say this electric field line is E1, okay, and the surface that you have taken is delta ds1, okay, this will be E1 dot ds1, right, cos theta, so it will be a dot product. Now, this is for phi, this is for what is the flux originated with this small surface. Now, I can divide the entire small surface into equal, like how this ds1 is, like that I can draw many, I can divide this entire small surface into these small ds, small areas, and I can see how much field lines are going through it. Okay, now since the area that I am taking is same and the field lines, the electric field lines in this case is, let's say the electric field lines through this is uniform, then the same amount of electric field lines will pass through each of this area. Okay, then you can basically make use of integration, or you can use summation, and you can actually find, right, you can actually find delta E, you can find it through the complete delta E, right? You can use integration to find the answer for this. So you find what is the delta, what is ds for a very small, what is the flux, electric flux for a very small surface, and then you use integration over a closed surface. Okay, this is possible only for a closed surface. What is the electric field lines? Okay, then you will get it for the entire surface. Alright, now on this note, with this basically gives you the idea of the electric flux. Now, electric flux, though it is a product of two vector quantities, electric flux is actually a scalar quantity. Why? For a given region, okay, we are not worried about what is the direction of the electric field lines in that case. We are just worried for a given space, for a given small region, what is the flux? How many number of electric field lines are passing for that given area? So what we are interested when we are talking about electric flux, we are talking about a magnitude. So though it is a product of two vector quantity, electric flux is a scalar quantity. Okay, the SI unit of electric flux is very simple. What do we have? Electric flux is basically phi E, right? This phi E SI unit is nothing but what is the unit of your electric field times the surface area, right? Unit of the what is your unit of the surface area, right? Here electric field unit is what? Electric field unit is Newton. Electric field lines is given by what is the force? If you keep a test charge in the presence of let's say there is a source charge, and let's say there is there is an electric field line around it. Now if you keep a test charge, okay, and if what is the force experienced by this test charge due to the source charge, that will give you the electric field lines of the source charge. So electric field is force per charge. Force per charge, force is nothing but Newton, per charge is Coulomb. Newton's Coulomb inverse 1. And area is basically what? Area we give it by meter square, right? So from here the SI unit of electric flux will be N m square C inverse 1. That's the SI unit of electric flux. Okay, so you need to understand what is the area vector. You take any area, draw a normal to it. Okay, then you can say this area moves in this direction. Area is a scalar quantity. Now you draw a normal to it and you can say, okay, this is the direction of my field. Okay, now this area moves in this direction, then you get an area vector. Now any region that is there, if you want to find out what is an electric flux. Flux, very simple. How many number of electric field lines are passing through for a given area? That gives you the electric flux. Okay, same concept will be used for to define magnetic flux as well. Alright, how many lines of forces are passing for a given area? That is basically your flux. Alright, flux, though it is a product of two vector quantity, it is a scalar quantity. Alright, now with this note, we are moving into what is Gauss's theorem. Okay, now this theorem just simply gives you the relationship, okay, between total flux that is passing through any closed surface. It works only for a closed surface, and the net charge enclosed within the surface. Okay, how many field lines, if you have a closed surface, let's say you have a closed surface. Now how many field lines are passing through this closed surface? And if so many field lines are passing through this closed surface, how many charges are there in that surface? That is just this relationship is basically given by Gauss's law. Alright, now the statement is very simple. You can define Gauss's law as the total flux through a closed surface. Gauss's law apply only for closed surface is 1 by epsilon naught. Epsilon naught talks about the permittivity, right? It talks about like let's say you have two charges. We did it when we did electrostatic force, Coulomb's law, right? So if you have two charges, right? Let's say I'm taking two charges, right? Let's say this is charge Q1 and Q2, and they are separated by a distance r, right? Now the electrostatic force equation is given by what? It will be given by K, right? That is electrostatic force constant Q1 Q2 divided by r square. Now this K value is nothing but 1 by 4 pi epsilon naught. Now what does this epsilon naught actually means? Now what are the ways in which you can change the force, right? You can change the value of Q or R, the force will change. Okay, now I have two charges separated by a distance. I am keeping this in vacuum. Now if I take the entire charge, the charges quantity remain the same, the distance of separation between them remain the same. Now if I take this entire charge and if I put it in water, okay, the electrostatic force changes. So what would have changed? The quantity that changed the electrostatic force right? That actually depend on the nature of the medium around it. Initially we kept it in vacuum, now it is in water, right? When we kept it in water, the electrostatic force changed. Now that particular quantity which changed the force, right? We basically say that that depends on the nature of the medium, is basically permittivity. Okay. Now from here we can say the total flux through a closed surface. Gauss's law worked for closed surface. The total flux through a closed surface is 1 by epsilon naught times the net charge enclosed by the closed surface. Okay. Now mathematically, how can we give this expression? Is 1 by epsilon naught times the net closed surface enclosed by this closed surface. Okay. Now mathematically we can say what is the flux through the surface, right? Electric flux. So we write E over here. Okay. This is the symbol we use for flux. Phi is the symbol we use for flux. Electric flux, we give it as E. Okay. Electric flux. Okay. This is nothing but mathematically we say the how much total charge is there. What is the total charge, right? What is the total flux? Total flux through a closed surface. So you write a closed integral, meaning for a closed surface, how many charges is there? What is the electric charge for a closed surface? Electric flux is given by how much electric field lines are flowing through for that closed surface we have considered, right? This is equal to, okay, the net charge times the 1 by epsilon naught, okay, 1 by epsilon naught times the net charge. Let's say the net charge enclosed by the surface is Q. Let's say there is a surface and let's say there is positive charges. Okay. If there are charges outside, doesn't matter. Gauss's law only applied for closed surfaces. So we only consider the charges. How many, because of the charges here, how many field lines are there? Okay. So the magnetic flux line is equal to 1 by epsilon naught times the charges inside. How many charges are there? There are 3 positive charges, right? Because of this, the charges outside doesn't matter. It wouldn't apply. So Gauss's law applies only for the charge inside a closed surface, right? So phi E is equal to the closed integral E dot ds, which is basically 1 by epsilon naught times QE. Right? You can actually give this as Q by epsilon naught. Alright. Now, if you want to study Gauss's, let's say we want to prove. What is the proof of this? Right? So to get the proof, what we are going to do, we are going to consider a positive charge. Right? So if you take a positive charge, the positive charge is spherically symmetric, right? We have seen this in the previous classes. So the positive charge will basically be, let's say you're taking a positive charge, okay? So this positive charge is going to have field lines everywhere around it, and in case of a positive charge, the charges will be radially outwards, right? Now, we are just going to take an isolated positive charge. There's no other positive charge. The field lines that are originated is only because of this one positive charge. Okay. Now, we are going to take a surface, right? We are going to draw a circle such that this circle has a radius. This circle has a radius. This circle has a radius r. Okay. And we are going to, there are field lines everywhere. We are going to take a particular surface, right? This surface that we are taking is basically called as the Gaussian surface. Okay. We are just taking around this point charge, there is a sphere that you are considering. This sphere that you are considering is basically a Gaussian surface, right? A Gaussian, spherical Gaussian surface. This you are considering is a spherical Gaussian surface. Now, what is a Gaussian surface, right? This Gauss surface is nothing but an hypothetical closed surface enclosing a charge. Is called the Gaussian surface of that particular charge. How much ever charges are there around the charge? If you draw a surface, these are just hypothetical closed surface, then that is called as your Gaussian surface. Now, this is chosen. Why do we need such a Gaussian surface? This is to evaluate the surface integral, okay, of the electric charge produced by a charge enclosed by it. Okay, so if you have a charge, right, if you have a charge Q, and if it has field lines going everywhere around it, right, it will have field lines going everywhere around in every direction. Right, so in this case we are just going to take a surface. This is a hypothetical spherical Gaussian surface around this charge over here at a distance r. Okay, now this surface, what it will do, it will just evaluate how much electric field lines is produced by this charge enclosed by the surface. Inside the surface, how many charges are there? We have just taken one charge. If there are multiple charges, how much ever charges are there around this particular sphere? How many charges are there? Okay, because of this charge, how many electric flux lines are produced by this? How many number of flux lines are produced because of this charge? So Gaussian surface, it's a hypothetical closed surface. It is just used to gives us, it just makes calculation easy. And using this, now we can simply say, if there is inside a closed surface, if there's a charge, how many field lines are there because of it? Okay, so that's the importance of your Gauss's law, right? By choosing a closed spherical surface, because Gaussian surface, in such a way that the electric field has a component which is either 0 or has a fixed value at every point of the surface, right? At every point, if you have a charge and if there is field lines originated, right? If you draw a Gaussian surface in such a way that at every point, either the electric field lines are 0, right? Or has a fixed value at every point on the surface. Okay, so we can easily calculate what is the electric field. Okay, I've just drawn a sphere. We are talking about a sphere, so it's in 3 dimension. Okay, so we can easily calculate what is the electric field, okay, of certain symmetrical charge distribution by applying Gauss's theorem. So one thing is, first of all, Gaussian surface is a hypothetical surface, but we are going to make use of it to calculate how many electric field lines are there. Okay, that particular charge, how much electric field lines it produces, right? And or what is the electric flux because of this, right? For a given area, how many field lines are passing through? That's what we want to find by applying Gauss's theorem. All right. Now, so this is the importance of a Gaussian surface. Now, what is the proof of Gauss's law? So we are going to take a charge, right? We are going to take a charge. Let's say this charge is Q, right? And this charge has, let's say this charge is Q, and this charge has field lines. Let's say this is a positive charge. We have taken a charge Q, and this is a positive charge. And this charge has a has field lines going everywhere around. Okay. Now let me just make this charge in the center. Let me just give this charge in the center. Okay. Let's say this charge Q, and this has field lines going in every direction. It has field lines going in every single direction. It has a field line going, right? An electric field line for a positive charge is always given, is always pointed radially. Right, it's always pointed radially outwards, right? Now, what we are going to do to prove Gauss's theorem, we are basically taking a Gaussian surface. This is a hypothetical surface, right? And this is a spherical Gaussian surface, the one we have considered over here. This is basically a spherical Gaussian surface. Okay, now from here, okay, now from here, what we are going to do, right? We just for simplicity's sake, we have taken one isolated positive charge, and we are going to keep this charge in the center, and we are going to draw a Gaussian surface such that from the center, right? From the center, if you take this radius of the sphere, right, from the center, this particular charge has a sphere. Let's say the radius, or this charge has this spherical surface has a radius r. Okay, now what we are going to do, there are field lines going everywhere around. So the number of field lines going at each, if you take a very small area on the surface, because this is a surface, think of a ball. There is a charge in the center of a ball, and there's field lines coming everywhere around. Okay. Now from here, what we are going to do, we are going to take a very small surface on the on this particular. From here, we are going to take a very small surface, right? Let's call this surface. Let's say this surface is just, the entire surface is S, right? And the small surface that we are considering, let's take that as ds. The entire surface is S, and the small surface that we are considering is basically would be ds, right? All we want to find is how many field lines because of this charge, right? On the surface we have taken this, right? So because of this positive charge over here, how many field lines are what is the flux because of this positive charge over here? That's what we want to know. For that, what we are going to do, first we are going to take a very small area, right, and through this area we want to know how much field lines are passing through this particular area. So first what we would do, we would draw a normal to this area, right? If this is the entire area I'm considering, this is the entire area that you're considering, the normal to this area would be, the normal to this area will basically be in this direction, right? Sorry, just a second. Right. So the normal to this area will be in this direction, right? This is the normal. So this basically give you your ds, right? At the same time, how is the electric field lines going? The electric field lines are also going in the same direction, right? The angle between them is basically 0, right? Now from here, if you want to find out what is the electric field passing through this particular point, electric field, okay, at any point, if you take any point on this particular surface, what will be the, at any point on this particular surface, anywhere you're taking, what will be the electric field line? That you can give by, right, electric field line. This we can actually give this by E is equal to 1 by 4 pi epsilon naught q divided by r square, right? This, since it's a positive charge, the electric field lines are pointed radially outwards, okay, at all points on the surface S, right? Now here the normal, that the area vector we have drawn with that of the electric field, these two does not have any angle between them. So if you look at the theta, right, area, these two are parallel to each other, right? E and the area vector, right, ds are parallel to each other, which means theta is basically equal to 0 degrees. Okay, now if you want to find, so because of this particular charge, the total field, what is the area, because what is the flux because of this point charge, and everywhere on the surface will be given by phi. But we are considering total surface is given by S. We are considering a very small surface, that is basically ds. Now what is the flux that is going through this ds? So if, for example, if 100 field lines are coming out of the sphere, now through this particular small area, right, some 10 field lines might come, right? For example, let's say like around 5 or 6 field lines are coming. Now that particular field lines, it doesn't represent the entire field electric lines or forces coming from this charge. It just represents what is the field lines coming out of the small area. Okay, so that we can give it as d phi. Okay, now the flux through this area ds can be given as d phi. Okay, electric flux, so we give it as de, right, can be given as E dot ds, right? Over here, E dot ds is nothing but, if you're writing the magnitude equation, it will be E ds into cos theta. Cos theta is 0, right? Cos theta, right? Here cos theta, there is no angle between them, right? So what happens over here? In this case, there is no angle at all. So all you will have is E dot ds. There is some flux line coming, right? There is no angle between them, but at that particular area, there is some field coming out. Okay, so this d phi E is basically E dot ds. Now this is the flux line coming from this. So now if I simply consider on this particular surface, just like how I have the small surface, because this charge is spherically symmetric, meaning the charge coming out is evenly distributed on the sphere. Now if similar to this, if I draw a small area over here, okay, the field lines coming through it, if 5 field lines are coming through it, if I draw this, let's say this area is very small, let's say it's 2 mm. Now again I draw another 2 mm surface, okay, the field through that again will be 5. Now if 5 flux lines are coming from here, because of this positive charge, if I draw a charge here, 5 field lines only will come at this point also. Okay, good evening. Alright, YS, right? Good evening. And yeah, we are covering, I'm just explaining Gauss's theorem. Alright, so you can always go back and just watch the entire class, right? So at the same time, if I take another surface over here, that is also, let's say, similar to this area, let's say it's again 2 mm. Then if 5 field lines are flowing in this plane, on this case also, if I draw a small area over here, this area also will have 5 field lines flowing through it, right? So again, if I take another 2 mm area, if 5 field lines are going through it, 5 field lines will through it, right? So how we can find? Now if I just find what is the area, what is the field lines, what is the flux on through the small area, right? Now I can make of integration, now I can make use of integration to find what is the total flux through the surface. The total flux to the surface is given by phi e, and that you can get it by integrating d phi e. Okay, over this entire surface, yes. Okay, now this d phi e will be what? Over the surface, entire surface. This will be over a closed integral, because Gauss's law applies for when the charge is basically under symmetry and there is a closed surface, right? Now for this closed surface, d phi e is given by E dot ds. Alright, now let's just do this in the next page, right? You have electric phi e, right? The total phi e is nothing but equal to the closed integral, right? S E dot ds, right? Now here E is constant, right? At every point at that small surface that you're taking, E, the number of field lines that is coming is constant, right? So we will take that quantity outside. And what about the area? This will be E into ds. So from here, the total flux, because of that point charge q, what is the total flux that you are able to see in the surface? This is basically given by phi is equal to E into integral, closed integral over the surface ds, closed integral ds over the surface. S is what? This is the total. This will just give you the total area of the sphere. Okay, this basically says we are taking, like, you know, a small, we are taking this area as ds, right? Like that we are taking another area ds over here, ds over here, ds over here. Like that we are taking multiple areas. Okay, and that will give you what? The total entire area of the sphere, right? What is this area of the sphere? Area of the sphere, total area of the sphere is given by phi e, right? Total area of the sphere is given by E is actually total area of the sphere is given by 4 pi, right? 4 pi area of the sphere, and this is radius is r, right? So this will be 4 pi r square. That is the total area of the sphere. And we know what is the value of E. E is what? 1 by 4 pi epsilon naught q divided by r square into, we have 4 pi r square. 4 pi and 4 pi cancels, r square and r square cancels. So phi E will be what here? Right? So here basically 4 pi and 4 pi cancels, r square and r square also cancels. So all we are left out right now is with q by epsilon naught. That's it. This proves Gauss's law, Gauss's theorem, which says the total flux, right? Which basically says the total flux through a closed surface, right? What is the total flux that is going through a closed surface is 1 by epsilon naught, right? It's 1 by epsilon naught times the charge enclosed by it. Right? So this gives you the proof of Gauss's theorem. So if you have any doubts, you can ask me. Right? And now we will be moving ahead with Coulomb's law. How can we deduce Coulomb's law from a Gaussian surface? Right? For doing this, we are going to do the same method. What are we going to do? We are just going to say there is a point charge, right? Let's say there is a point charge. This is an isolated point charge Q. Okay, because of this isolated point charge, there is going to be field lines everywhere around it. There is going to be field lines, right? This electric field lines will always be pointed radially outwards, and there will be field lines everywhere around the charge. There is going to be electric field lines. Right, now what we are going to do, we are just going to choose right now this charge is there, around it, everywhere around there is radial fields coming out of it. Okay, this is the electric field lines that is coming. Now we are going to choose a Gaussian surface, right, such that this particular surface that we have chosen is a spherical Gaussian surface, and again it is at a distance. It is at a distance r from the center. This Gaussian surface, this is the spherical Gaussian surface we have chosen, is it at a center r from the center. Okay. Now what we are going to do over here, let's say, okay, let's say this value, this one over here is r. Now what we are going to do is we are going to take a very small area. Okay. Now Gauss law works for spherical symmetric, right? This means the electric field lines, okay, on the surface, this particular Gaussian surface we have taken, let's say the surface is S, right? On the surface over here, right? If you take a very small area, if you take a very small area over here, very small area over here, likewise, okay, wherever you go on the surface of the sphere, if you're taking a very small area. Okay. Now this is a sphere. Since I've drawn a circle, it looks like 2D, but imagine it's a ball and the charge is in the center. Now everywhere on the surface that you're taking, the electric field line, the magnitude of the electric field line, so if there are 5 field lines passing through this space, there will be 5 field lines passing through that particular surface, if the area that you're chosen is the same everywhere. Okay. Now so the magnetic field lines through this particular area is going to be same, right? So if I take an area here, you can say one field line is flowing, but in this case I've drawn just very small number of field lines. But if you see, the number of field lines that are there will be actually more, right? Now in this case you're taking a Gaussian surface. Now from here we know since it's a positive charge, the electric field lines will go how? The electric field lines will actually be pointed radially outwards in this direction, right? Now to study what is the flux through it, what we are going to do, we are going to just choose one small area. We are going to choose very small area over here. Let's say this is the area that you're choosing. Okay. And for this particular area, you want to find out what is the flux lines? What is the flux like? Right, for this particular area that we have chosen. Right. So if this is the area that you're choosing on the surface, so this particular area will also have a normal vector to it, right? So you have a surface on the sphere, you're taking a very small surface. Now this will have a normal vector to it. The normal vector to, let's say the entire surface is S. Let's say this surface that you're chosen is ds. So the normal vector, you will give it as, the normal vector will be ds in this direction, right? It will be in the direction of the electric field, right? So what will be the flux because of this? No, we're not talking about the entire flux. We are interested in the small surface that you're seeing over here. How many? Because of this charge that is inside this closed sphere, right? In this surface over here, in the small surface over here, how many field lines are passing through? That is what we want to find out. Okay. Now that can be given by, right, that you can give it as d phi e, right? Because total flux is phi e, but because of the small surface, how much flux is there? There will be very limited flux, right? So in this case, it will be d phi e. This will be equal to e dot ds, right? In this case, what happens? There is no angle between them, right? Cos 0, angle between them. Cos theta is basically 0. See, ds and e, right? The area vector with that of the electric field are parallel, which means there is no angle. So in this case, if you write e, this will be e ds cos theta, right? Cos theta. Now cos theta in this case, theta is basically equal to 0 degrees, right? There is no theta at all. Cos 0 is 1. So e ds cos 0. Cos 0 is basically 1. So all you will get over here is e into ds. Right? So you will get e into ds on this point. Since angle is 0, so you will get d phi e. D phi e is basically equal to e into e ds. Meaning, what is the flux through this particular surface? That is, flux means how many lines of forces are coming out of the small area over here. That will be the flux through it will be how many magnetic field lines are passing, how many electric field lines are passing through the small area ds. That will be the flux. Okay, this is for this particular area. Okay, now we have found what is the flux for a small area on the surface, right? Now if you want to find for the entire surface, then we make use of integration. Right? So then we say for the net flux through the entire surface S, that you can find by taking phi e, right? That is basically you get that by integrating over the closed surface is d phi e. Okay, what is integration of d phi e over this entire surface? This is nothing but E dot ds, right? E dot ds in terms of magnitude, if you're writing E dot E ds cos theta is 0, so we have seen that, so it will be just E ds, right? This is the surface. Now over here again, at every point on the surface, the electric field lines coming are same. So if you draw similar surfaces, like I explained earlier, if you draw similar surfaces everywhere on the surface of the sphere, if for this particular, let's say you considered for example, you've considered this area is 2 millimeter square. For example, the area is 2 millimeter square, and if 5 lines are coming, if you take another area which is 2 millimeter square, there will be another 5 lines only coming through it. Another area somewhere over here, 2 millimeter square, there will be another only 5 lines coming through it. So you can say this entire surface is made up of this ds element. So if I take 2 millimeter square area, we put it together, I'll get the entire sphere. Now, so using integration over here, the magnetic field at any point that I'm taking, the magnetic field lines coming out of this out of those particular surface is same. If only 5 field lines are coming through one surface, the other surface that you're taking, since the area that you're considering is same, so the electric field lines coming out of the surface is also same. So because of that, we can actually take the electric field line, because it's constant, right, for a particular surface. You can take that out. So you will only have closed integral EDS into ds, right? So from here, what can you say? Phi e will be what? Will be basically E into closed integral ds. Closed integral ds is nothing but it just tells you about the area. What is the total area of the sphere? This will be what is the total area of the sphere, right? Total area of that particular sphere would be 4 pi. The radius of the square is r, right? So 4 pi r square. So d phi s, this element is just total area of the sphere. Okay, now we know what is, okay, from here this is basically phi e, right? Now using Gaussian theorem, okay, using Gaussian theorem, we know this phi e is equal to q by epsilon naught. That's what the Gaussian theorem says, right? That was the proof of the Gaussian theorem. Now you have flux for one surface, and then we know the flux of the surface that we considered over here, right? Now using Gaussian surface, this is what you can do using Gaussian surface, right? Now you have two quantities. Now you can equate them. From here you can write this E into 4 pi r square is equal to q by epsilon naught. Phi is equal to phi, right? You can equate both of them. Now from here what you can write, E is basically what? 1 by 4 pi epsilon naught q divided by, right, 1 by 4 pi r square, 1 by 4 pi r square q divided by epsilon naught. I'll just rearrange this and write this is nothing but 1 by 4 pi epsilon naught q divided by r square. This just brings back the electric field equation, right? Okay, now to get the Coulomb's law, what we are going to do, we are going to take a point charge and we are going to keep on the surface, right? Now on the surface we are going to keep a point charge. Let's say somewhere on the surface I'm going to keep a point charge. Point charges are positive unless otherwise specified. So as soon as you keep a point charge, what happens? Now the distance between them is what? You kept a point charge over here. Let's say the point charge is basically q naught, right? Now point charge q naught, the distance between them, let me do one more thing. So instead of writing it on this surface, let me say I'm keeping a point charge on the surface, and this is basically q naught. Now what is the distance between them? R. So as soon as you keep a positive point charge, right, you're keeping a test charge over here, the source charge is positive, the test charge is also positive. So what will happen? The test charge will experience a repulsive force, right? The test charge will experience a force in this direction. Because of the source charge, the test charge will experience a force in this direction. It will be repelled. It will experience a repulsive force. So how do we write that? The force experienced by the source charge because of the source charge, the force experienced by the test charge because of the source charge will be electric field times the charge, right? We know electric field is given by force per charge, right? So force was given as charge per electric field. right? What is the electric force experienced by the what is the electric force, right? What is the electric force experienced by this test charge because of the electric field lines of this source charge Q? Right? You can actually use this equation because we know what is the electric field lines over here will be given by force per test charge. From there you can get force is equal to Q naught into E. Right? So now already we know E, right? And we have this equation. So F is equal to Q naught into what is E? E we just found over here. Electric field line is given by 1 by 4 pi epsilon naught Q by R square. So from here F is what? 1 by 4 pi epsilon naught, right? Q naught divided by R square. Okay. This is nothing but this just talks about the electrostatic force between the two charges, right? When you keep this charge on the surface, what is the electrostatic force it will experience? It will experience a repulsive force because it's a positive charge will get repelled in this direction, right? It will get repelled in this direction. So now from Gauss's theorem, we have actually got electrostatic force equation. So this is deduction of electrostatic force equation from Gauss's theorem. So this proves Coulomb's law. Okay, this actually proves, using Gauss's surface, we can actually prove Coulomb's law as well. Okay, with this note, we are coming towards the end of the class. Right, so okay, what we are going to do is we'll just do a very small one simple question, okay, taken from one of the reference books you have, right? So basically, let's say there is a positive charge. Okay, let's say there is a positive charge, and let's say this positive charge Q is equal to 17.7 microcoulomb. That is the charge on the positive charge. Okay, now this charge is placed on a hollow sphere and the radius of the sphere is basically, the radius R of the sphere is 0.5 meters. Now if you want to find out what is the flux through the surface of the sphere, you want to find through the surface of the sphere what is the flux. Inside it's hollow, there is only 1 point charge, but on the surface what is the flux. Okay, this you can make use of Gauss's theorem because according to Gauss's theorem, phi is equal to charge by 1 by epsilon naught times the charge. The flux passing through through the Gaussian surface, this is given by, the total flux passing is given by 1 by epsilon naught times the charge, right? So from here, what will be 1 by epsilon naught, right? 1 by epsilon naught is what? This is 17.7 into 10 to the power of mu is what? Minus 6 coulombs, right? By epsilon naught, what is the value of epsilon naught? Epsilon naught value is constant, right? 8.85 into for free space is into 10 to the power of 12. From here, this is the flux. Okay, this is 2 into 10 to the power of 6 Newton Coulomb meter square C inverse 1. But we want to find what is the flux density through the entire surface. Okay, so if you want to find out what is the flux density will be total flux. We have found the flux, total flux by area, right? So from here, what is the total flux? Total flux we actually found 2 into, total flux is 2 into 10 to the power of 6. Okay, what is the area of the sphere? Area of the sphere is 4 pi into R square. What is R square over here? R is 0.5 meters, right? So this will be 4 pi into 0.5 square. So if you solve this, you will get the total flux, flux density, right? This you will find the flux density to be equal to, right? This will be 6.4 into 10 to the power of 5, right? This will be 6.4 into 10 to the power of 5. What is the unit? It will be Newton per Coulomb because it's flux density per area. So Newton per Coulomb, meter square gets cancelled. Alright, so with this question we are coming towards the end of today's class, right? So once again there is an ongoing batch. I am really sorry once again about this. Okay, this is not an upcoming batch, this is an ongoing batch now because the batch started on June 1st, right? The mode of delivery of this batch is going to be English. So the target of this particular batches, this particular course is very simple, right? We want to cover your entire midterm portions. So midterm portions, again, it will be the first 5 units of your term 1. That's what we're going to cover in this course. Now, when you buy any subscription with Unacademy for ISC Board class 12, you are getting a course. So you are paying for math, physics, chemistry and biology. For physics, we would be meeting every Monday, Wednesday, Friday between 5:15 to 6:15 p.m. Okay. Now, whatever subscription that you're taking in this case, right? In this case, if you're taking in case you're taking physics, minimum of 10 classes will be there in a month for physics, for math, for chemistry and biology. Minimum 10 classes. Other than this, you will have weekend test series will be there, right? Every other weekend there will be a live test series, and there will be analysis session for the same as well. Now, this is the minimum number of classes I'm talking about. 10 classes will be there for you for a month. Now, the timing is for duration for each class is 1 hour. Okay. And whatever subscription fees you're paying for, if you're using my code MTIS10, you'll get a 10% discount on the same. The longer duration you take the class, for example 1 year, then the price per month reduces. Okay, so you can use my code MTIS10 to get a 10% discount on the same. Alright, and also if in case you're in class 11, in any case, if you're class 11 student, if you're coming across this, if you're taking a class 11 subscription, class 12 subscription is entirely free for you. You're just paying for 1 year, but you're getting 2 years worth. Right? At the same time, we have a community feature. So this is the link to my community. If you're in class 12, try going to the community. There is many questions, right? MCQ type questions I've asked. You can try attempting them. So these questions will be from the first 4 units, right? And so you'll never miss. Also, if you're in the community, you will never miss any updates from your educators, right? And also you can directly give feedback to your educators via tool. Alright, and also if you're coming across any inappropriate content and if you're reporting the same, then you can claim a prize as well. And with this note, we are coming towards the end of the class. If you have any doubts, you can ask me. I'm happy to stay back and answer. Otherwise, you can, if you like the class, like and share the class, right? The class video, and also subscribe to the channel and click on the bell icon. So when the next class is coming also, you will be notified about the same. Alright, okay then, thank you for taking the class.